Hi students, welcome to preliminary chemistry and the water topic. This is the last little section in the water topic when we're looking at issues related to the heat capacity of water, a nice lead in to our final topic on energy. So in this video we're going to focus on specific heat capacity. So firstly, a definition: the specific heat capacity of a substance is defined as the amount of heat in joules required to raise the temperature of 1 gram of that substance by 1 degree Celsius. There's a couple of important things with this particular definition. Firstly, you will find that the calculations that you're going to be undertaking in this topic are going to involve temperature in Kelvin. Now, whilst the starting point of the two scales, Celsius and Kelvin, are not the same, the increments are. So a change of 1 degree Celsius is equal to 1 Kelvin, and that's kind of the important thing here, even though 0 Kelvin is the same as minus 273.15 degrees Celsius. So there are some absolute differences, but when we're looking at the differences, there are none. So as a consequence, if we look at the fact that water has a specific heat capacity of 4.2 joules per gram per Kelvin, then what we're saying is that if you have 1 gram of water, which we know from water's density is also equivalent to 1 mil of water, and you want to heat that up by 1 degree or 1 Kelvin, then it will take 4.2 joules of energy in order for you to do that. Now, that value on its own may not mean very much, but what you'll see through this particular video is that's actually a very high value, and there's some interesting consequences as a result of it. So the first thing to do is to look at why that value is so high. And if you think about it, keep in mind we're looking at 4.2, 4.18 joules per gram per Kelvin for water, and then compare that with each of these others. You'll find mercury, which is liquid at room temperature, 0.14 heats up very readily, very small amount of energy to raise 1 gram of it by 1 degree. Air has a specific heat capacity of 1, dry soil 2.2, and ethanol, key component of alcohols, is 2.44. So you can see this value for water is a significantly high value in comparison with some of these other substances. So what? Well, this is the so what. Water's high specific heat capacity enables it to absorb lots of heat or energy from the sun without a significant rise in temperature. You know that if you're a surfer, because you know that the temperature in the water varies much less from across the course of the year than the temperature on land does. So this makes aquatic environments a much more stable environment for organisms that live in them. Those smaller temperature ranges mean that they don't have to have quite as many strategies in order to regulate their temperature as organisms that live on land. And that can be a range of different types of strategies that are used to do that. And we don't need to go into those in this course. If you're doing biology, you certainly will. And you may already have looked at some of those at this point. But for our chemistry purposes, all we need to recall is the fact that water has a very high specific heat capacity. This means that it takes a long time to warm up. It'll absorb a lot of heat without rising, a lot of energy without rising a lot in temperature. It also means it's going to lose that quite slowly as well. And that means we get a lot more stability in our aquatic habitats than we do in our terrestrial ones. We're going to move on to some calculations that involve this specific heat value and how we can actually measure what happens to water as we add or subtract heat energy from it. But that's coming up in future videos. Thanks for watching.